tried hard, but where did we so long? I hope we could, but I won't start over again. Midday street war outside, smelling dispersed in the air. Nobody stopped to sit and wait. Your light seems so innocent. Everything made sense to you. They didn't do me. Heaven
Hi, everybody. Welcome back to Chem 131 for what is the last week of classes. As that last track seemed to imply, time goes really fast. Whether you're enjoying it or not. Hopefully, the quarter has been enjoyable and not too ridiculous. Like this cat that just appeared at my feet because I started talking to you guys. That's the wrong window. There we go. That's the one I want. Maya, go away. All right. So today we're going to talk about lab worksheet number 5, and really, this is kind of just a 5-minute explanation of it. I had a different lab that I was planning for you all to do. Kind of at the last second, I decided that instead of doing a lipids lab, I was going to do this instead because I had 2 labs to pick from, and when I saw this experiment, I thought, I don't really want to just show you a video and then have you answer questions about it. But it turns out that the process is kind of interesting. And the Lipids Lab was yet again another, oh, what lipid do you have? Well, dump in all these things and choose an unknown, except there were like 2 unknowns. So it would have been kind of just busy work. I mean, we've already done 3 of the labs so far involving just like ID the unknowns. Can you do it? Can you do it? Good, you did it. That sort of thing. So this is different. We're going to talk about casein, which is a protein in milk. So casein is kind of this interesting substance that's been used for a long time in various capacities. So, like for instance, you can use it to make cheese. But you can also use it for things like organic-based glue. So, like Elmer's glue used to have casein in it, and the properties of this specific protein, which we haven't really talked about proteins yet because that's tomorrow. Proteins are amino acids. So just to go really quickly to this right here, we could draw a basic protein like this. So on one side of the, oops, that's not the pen. Sorry. On one side of our protein, we have an amine group. And on the other side of our protein, we have a carboxylic acid. And so when I have a molecule that has these 2 things together, what we call it is an amino acid. Now, I have left out one very important part to my amino acid, and that's actually this right here. So, I have a chiral carbon, and on that chiral carbon is going to be a hydrogen, and then an R group. And the R group is going to be one of 20 variations. And so these are called the amino acids, where you replace R with, maybe it's hydrogen, and then that molecule becomes glycine. Or maybe it becomes methyl, and I think that that's alanine. I don't have the amino acids memorized because why? Just look them up on the chart, right? So I will be giving you the chart of amino acids, and we're going to be talking about that tomorrow. And my goal in this class is not for you to memorize amino acids or their names. Like, I know all the names of them, but I couldn't match them with structures because I don't really care about that. You can just reference that. What's more interesting to me is what do those structures do, which is kind of what the whole point of this class is. So if you had an amino acid where R was a hydrocarbon with an OH at the end, what could that do? Oh, it could hydrogen bond to stuff. That's interesting. What does that do for proteins? That's what we're going to talk about. Oh, it has a thiol group in it with a sulfur. I can make a cysteine bridge out of that. Or I can make this charged, like it's L-arginine. I can put a proton on it. Now, makes a salt bridge because it's an ionic chain. Those are the sorts of things that we're going to care about. Now, if I take a bunch of these and I sort of just chain them together, then I get something that looks like this. Oops, not O. That's not what's going to go there. So N, carbon, carbon, double bond O. And then this would go on forever and ever and ever and ever. And this could go on in this direction too. So this would be 1, 2 subunits of what would be called a peptide. And if I get a bunch of these together, I would call it a polypeptide. And then when those things arrange themselves in a three-dimensional structure, the result is called a protein. So in tomorrow's lecture, when we actually discuss proteins, we're going to be looking at this first in the sequence that we construct, because we're going to be constructing this sequence out of just randomly choosing 20 different amino acids. And then we're going to start allowing that chain that we've made to kind of twist around, because these are all single bonds. So they can all rotate however the heck they want to. I could eventually make my molecule just kind of loop around on itself. And a lot of the times in proteins, it turns out molecules will do that. Because if my molecule is soluble in water, I can transport it. But if it's too soluble in water, then I can't use it for things like structure. So, for example, your muscles can't be soluble in water. That would be bad. Every time you drank water, or water moved through your body, all of your muscles would dissolve, and you'd become like a blob, right? You'd be Zack from League of Legends, or something like that. I don't know who plays that, and I don't even know if that's right. I know that character. He's a blob. So obviously that's not desirable. So there are reasons for proteins to be both soluble and also insoluble, depending on what the structure is that you're looking at. For example, hemoglobin is a protein. You want that to probably be soluble, otherwise you can't transport oxygen in your bloodstream. Like, that would be bad. All of that and more we will cover in the lecture tomorrow. But we're going to be talking about casein here for this experiment. Now, casein is what's called like a storage protein, and what that means is that the point of it is that you digest it, and when you digest it, you get the nutrients inside. So you hydrolyze the protein, you get to have the amino acids, and then your body moves them around to where they need to go for whatever cellular structure or keratin or whatever you need to make. Because it's a protein, it follows the principles of all other proteins. You can play with the pH, and you get a different form. If the pH is really low on a protein, we'll go back over here to our diagram here. I'm going to just copy this protein down here. If the pH of a protein is really low, then what that means is that there is lots of H plus in the solution. And we can put H pluses anywhere on the molecule that will take them. Excuse me. Now, the carboxylic acid already has an H on it because it's an acid. It's supposed to give the H and that, right? But if I have tons and tons of this, I'm going to drive the reaction back in this direction. That's from 121. So in a low pH solution, I'm going to put H everywhere I can, which means that I'm going to have this be protonated. Now, over here, this is a base. Bases accept H plus from the solution. So what this will end up doing is this will actually take an H and be like that. So that's at low pH. At high pH, where there's very little H plus available, here's our amino acid here. if there's very little H, like you can see up here, then the reaction would be driven in this direction, and I would have this form. So this gets deprotonated at low pH. And then for our base here, bases don't lose H+, they absorb it. But if there's none to absorb, because it's high pH, we just leave it as is. So you can see there's a difference here. At low pH, the amine part is charged, and at high pH, the carboxylic acid side is charged. I should say carboxylate because that's what it is now. Now, due to the Goldilocks principle, there must be some pH where this is just right, where I'm somewhere in the middle. And there totally is. But the form that exists in the middle is not the neutral form. In fact, it is the both sides are charged form. And the reason for that is because if one side is acidic, one side is basic, I'm just going to pass my H+ over from one side to the other. And doing that gets me a charge on both sides. This is called a Zwitter ion. And it occurs at the isoelectric pH point. In other words, at some pH, my protein has charges on both ends, and the overall total charge is 0. At other pHs, higher or lower than that, the protein will be charged on the side or end based on what pH we're looking at. So if it's low pH, the amine side will have a charge because it picks up a proton. If it's high pH, the carboxylate side will be charged because it gave away its proton long ago. Now, why do we care about that? Because when we isolate casein, we're going to make it so that it exists at the isoelectric point. And when that happens, we get an interesting little sort of setup. My proteins are shaped in such a way that I can then stack my proteins in a sort of orientation that looks like this. So I have my positive side, which is the amine, will stack next to the negative side of a different protein chain. And if I get a bunch of these together, I can make sort of what looks like an ionic compound, at least in one dimension. And I can align these however I want to. I can align them horizontally or vertically. I can even align them back to front. I'm basically making a sort of ionic lattice with organic parts to it. And so what ends up happening is that if I get the pH to whatever the isoelectric point is of casein, then it becomes insoluble in water. And if it's insoluble in water, I can filter it out. And so that's what the experiment is going to do. So I've provided a few videos for you of this process. And what you'll do is you'll watch them. Oops, I don't want to click on that because it'll change my screen here. Watch the two videos. Make sure you have subtitles on for the first one because the first video is the one I was given. And in my opinion, and I have a hard time like hearing through a headset or listening to something when there's an audio, or not an audio, a visual component going on. Using the subtitles will help a lot. Of course, then what I do is I just read the subtitles and then I miss the video. So you might have to watch the first video once or twice. The second video is, I thought it was a little bit better because instead of having a bunch of pictures just flash by of the process, you actually get to see somebody do the experiment where they add the material and then you see the casein precipitate out. And then you see it get filtered and you can see how this process is going on. I think the first one is more informative, but the second one is more visual. So use both of them, and then you're just going to have a bunch of questions here. So some of these questions can be answered before you watch any videos, and that's totally fine. Some of the questions may require you to look things up. So, like, for example, what causes milk to be white? I don't really talk about that. That is a little bit common knowledge. So a lot of people think, oh, I know exactly what this is. And you can state that. But what I do want you to do is be very sure of that. Go look it up and see if you can find something to support that. Surprise, you get to do math. There is one math problem here that asks you to calculate the percentage of casein in milk. And so if you figure out the mass of casein and the volume of the milk used, you could figure out a mass volume percent. One of the videos will show you the experiment where they do that. They'll say, oh, we put this much milk in, we got this much protein out. So do the calculation. And then down here, how many grams of this protein are in a cup of milk? So if you have a 235 milliliter cup of milk, how many grams of protein are in there? You could solve that now. And then I tease you about significant figures, which I showed this to my other students in my other classes who they care about sig figs. We don't give a shit about sig figs here. This is organic. We are much more interested in the chemical properties of stuff, which is why I made you learn all those functional groups. And we never asked you how many sig figs are in the number 10, like, because who cares, right? We did that at 121. Nobody liked it. Nobody cared about sig figs. Everybody got them wrong. They're important, obviously. I'm just being silly here. But in this class specifically, it's not the focus at all. So if you could just give me a number and do the calculation correctly, I'll give you your points for it. You'll notice there's only 10 questions, and each question is worth 2. So by doing the assignment, you get 5 points. So it's still worth 25. However, I've already given you 5 points. However, to get those 5 points, you do have to turn in the assignment. So if I get a no submission from you for this lab, you don't get those 5 points. Even if all you do is turn in a blank copy, I'll still give you 5 points. Like, if you panic at the end of the quarter, like, oh shit, I don't have enough time, I didn't watch the video, the final exam's tomorrow, whatever, I'll just get 5 points. Like, that's fine. You could do that. Is this lab due tomorrow? No. So the lab number 5 is due. Let me get the syllabus out real quick. It's at the end of the syllabus. I believe I take this one day after the final exam is when I intended to... Oh, I didn't mean to click on this one, but you could see it now. Where is my schedule? There it is. Oh, it's one day before the final exam. Okay. So next Tuesday is when this is due. So same as before. You get a week and a day to do it. So the soft deadline will be Tuesday. The last call will be the day of the final. So don't let those two things stack on top of each other, because if you're doing the final and you're like, oh shit, I didn't do the lab, you're going to get 5 out of 25, and that's no good. So make sure you do this. Probably get it out of the way sooner rather than later. After you do the proteins discussion tomorrow, and then on Wednesday we're going to finish that up and talk about nucleic acids and stuff, you're going to be in great shape to do this, because this lab is... I mean, the labs in this class are kind of standalone. I think for the first few experiments, like, it definitely helps to have seen the material. But as we've gotten further and further in the course, the content becomes more independent, I think. That's really all I have. That's the assignment in its entirety. So you're going to answer those 10 questions. Again, work together. Use the Discord and talk to each other. If you have a question or a source that you don't understand, or you can't see what's going on in the video, or if you just have other generic questions for me, let me know. Okay, yeah, that's all I got. So, I'm going to let the music play some more while I let the chat populate with any questions that people might have. So if you have any questions about this lab or the class, or want to go over specific questions on topics, let me know. I'm just going to put this screen up for a little bit. And let me get the music back up here. We're doing Persona this week, which means J-pop for days, basically. Alright, so I'm going to hit play. Put any questions you might have in the chat. And I'll check back in about 5 or 6 minutes. And we'll see if we can go over any of those.
I'll put you in a trance and let's party. Boogie in your body. Work that body. Make sure you don't hurt nobody. I say, hey, feeling the fire with a burning desire. Yeah, get up off of that thing. Dance and shake and let's swing. Come on, girl, let me rock the world. While I put you in a trance and let's party. Boogie in your body. Work that body. Make sure you don't hurt nobody. I say, hey, feeling the fire with a burning desire. Yeah, get up
covers all society. Damn right, mommy's not here, gonna fight all night. Right here, shadow 10 o'clock direction. Seize the moment, this destroy the nation. You rhyme slow motion, give me motivation. Breathe out now, and then I'm a rival. Round up around, spit out all over. Rhyme like a rolling stone, calm in the crowd. Watch out the moon, they diss you loud. This was this sound, and bombs hold ground. So round up, don't ease your pace, cause enemies brutal. Moment of truth, there ain't no truth. You're the only one world, one love. But the battle goes on, shadows all mass destruction.
Oh yeah, down, down, baby, baby, down, oh yeah, down, baby, baby, oh yeah, down, baby, baby,
Battlegrounds right here. It's a man's world. Gotta get ready for this right here. Hey yo. Here's a wake, anger breathes loud, face reality. Never be charity. The enemy you're fighting covers all society. Damn right, mommy's not here, gonna fight all night. Right here, shadow 10 o'clock direction. Seize the moment, this destroy the nation. You rhyme slow motion, give me motivation. Breathe out now, and then I'm a rival. Round up around, spit out all over. Rhyme like a rolling stone, calm in the crowd. Watch out the moon, they diss you loud. This was this sound, and bombs hold ground. So round up, don't ease your pace, cause enemies brutal. Moment of truth, there ain't no truth. You're the only one world, one love. But the battle goes on, shadows all mass destruction.
oh yeah, down, baby, baby, oh yeah, down, baby, baby, oh yeah,
Battlegrounds right here. It's a man's world. Gotta get ready for this right here. Hey yo.
Hi everybody, I didn't see any questions in the chat, so if you have anything to ask me, let me know. Last call, and I'll take the stream down in about a minute or so here. Otherwise, see you tomorrow for lecture.